Okay, everyone, and thank you for coming. Welcome to our fourth Climate Snack. For new people, Climate Snacks are informal conversations on climate-related topics in a format that is hopefully accessible to everybody, including non-scientists and scientists from other disciplines as well. Today, I have the pleasure to host Sara Vicca from the University of Antwerp in Belgium. Sara has published many influential papers in most of the top journals on topics mostly related to carbon and nutrient cycling in terrestrial ecosystems, with a strong focus on climate change, and more recently also on nature-based solutions for CO2 removal. I have collaborated a lot with Sara, and it's a joy to work with Sara always. Today, she would talk about carbon sinks, policy, and nature-based solutions to slow down global warming. And we will have a Q&A section at the end. So please feel free to start formulating questions in the chat box during the discussion. Sara, whenever you're ready, and thank you for being here.
Thank you, Cesar, for the invitation. I'll try to share my screen now. Okay, you see it?
Yes.
Okay, so yes, thank you all also for being present here. I'm glad to present a general talk, actually, for like non-specialists also, on interactions between land ecosystems and climate change. So let's start with getting the main cause of climate change clear, so that we're all on the same page, which is, of course, the emissions of greenhouse gases by human activities, by burning oil, gas, and coal. We emit large amounts of CO2 and also of methane and into the atmosphere. And besides burning of fossil fuels, also deforestation is an important cause of greenhouse gas emissions, especially of CO2. And due to these continued emissions, atmospheric CO2 concentrations have gradually increased from around 280 ppm, so ppm stands for parts per million, of CO2 before the Industrial Revolution to about 420 ppm CO2 today. And because greenhouse gases trap heat, they keep the earth warm, and temperatures have increased due to these increasing greenhouse gas concentrations, as you can see on this figure, with the temperature evolution over the last 2000 years. And well, there's a lot more happening than just a temperature increase. We're already observing an increase in the frequency and intensity of extreme heat, and also heavy rainfall events are increasing in frequency and intensity. We also get more droughts, and droughts and heat combine to increase fire weather. So that's weather that stimulates wildfires. And this slide is from the new IPCC report that came out. Well, this is from the first part of the report that came out in August last year. So extreme events, extreme weather events increase, and well, let's just refresh our memory a bit and look back at the summer of 2021. We're already in May. Large parts of Siberia were burning during a severe heat wave. At the end of June, a killing heat wave hit Western Canada and parts of the Western US. Temperatures reached almost 50 degrees Celsius there in Canada, in Lytton, and fueled a wildfire that destroyed the town. A few weeks later, it was Europe's turn and Turkey's turn to be hit by a severe heat wave and to experience lots of wildfires.
So Sara, what you're showing is evidence that the effects of climate change are already happening now and quicker than we initially thought, and that these changes are not only affecting temperatures and humans, but also affecting ecosystems. And as we've talked in this climate series, vegetation play a very important role in regulating the climate and in slowing down climate change. Could you please talk a little bit about your research and research in general about the role of ecosystems in regulating the climate and why that's important?
Yeah, I was gonna get to that. Well, maybe I skip this then. Actually, natural ecosystems have been working as a brake on climate change. And without that brake, climate change would have been much worse already. And you can see that illustrated on this figure. You see my pointer? So on this figure, on the left-hand side, you have the anthropogenic CO2 emissions. So CO2 emissions resulting from burning coal, oil, gas, and also from land use change. And if all that CO2 would have stayed in the atmosphere, we would now have atmospheric CO2 concentrations of about 600 ppm CO2, and we would have passed already the 2-degree warming threshold. Sorry. But due to our natural ecosystems, the land and the ocean, that have been soaking up much of the CO2 that we emitted, we're only at about 410 or 20 ppm CO2 right now. So more than half of the CO2 that we have emitted in the past decades has been absorbed by these natural ecosystems. And well, my work focuses on how this happens on land. And well, land ecosystems have sequestered about 30% of human CO2 emissions. And several analyses have pointed out that this is primarily due to the CO2 fertilization effect. We know from lab experiments and other experiments that exposing plants to higher CO2 concentrations makes them grow better, as is illustrated on this figure. And also in observational data sets, we see similar effects. For example, in one study on temperate and boreal forests, where CO2 fluxes have been monitored for multiple years, we found an increase in photosynthesis and in net carbon uptake with increasing CO2 concentrations. Besides the CO2 fertilization effect, which is responsible for about 70 to 80% of the increase in the land carbon sink. Also, other factors have played a role, like forest regrowth. For example, after the collapse of the Soviet Union, the abandonment of agricultural lands in countries such as Moldova, Hungary, Croatia, which you see on this figure, allowed the forest there to regrow. And well, in Russia, for example, more than 40 million tons of carbon were sequestered every year for several years in the late 90s and early 2000s. And that's equivalent more or less to about 10% of the Russian CO2 emissions. And then a last important factor that has contributed to this increasing land carbon sink is nitrogen deposition. So fossil fuel burning and also fertilization in agriculture lead to emissions of reactive nitrogen. And this nitrogen travels through the air and falls down on the land, for example, when it rains. And this nitrogen fertilizes our ecosystems. And so it makes the plants grow better and profit more from the increased CO2 concentrations also. So for the carbon sequestration, this is a beneficial thing. However, nitrogen deposition also causes acidification and is has adverse effects on biodiversity, for example. So it's definitely not something that we want to stimulate. But yeah, it has been positive for the land carbon sink globally. So over the last decades, land ecosystems have put a brake on climate change by absorbing much of our emissions. But a key question now, as climate is changing, is how long this effect will remain, how long we can rely actually on the land ecosystems to slow down climate change. And well, there's several threats to this land carbon sink. Yes, I take these extreme events because they are really important, having an important effect on our land ecosystems. There's also other factors like just the gradual warming that affect carbon sequestration on land, but these extreme events, they can really have very strong effects. And especially wildfires are an example of extreme events that are obviously a threat to the land carbon sink. Here I put some figures from Science Brief, which is a platform that collects available literature to answer scientific questions on climate-related issues, such as what the impact is of climate change on wildfires. The figure below shows our groups the studies on climate change and wildfires according to their findings. The y-axis is the publication date. And you see that over the last more than, I don't know, 10 years almost, there have been several studies published that support the claim that climate change is increasing the risk of wildfire. The figure on the right also shows this. It's from a study where they analyzed the changes in the fire season length, or the fire weather season length. So when we have weather that is hot and dry and can stimulate fires, wildfires. And there too, you see that there are several areas like the Amazon and also California, Western US, where there has been a clear increase in the length of the fire season. And well, wildfires can have a strong effect on the land carbon sink. And to illustrate that, I'll take you back to July or to the summer of 2019, where first in July in the boreal forests, there was a strong heat wave that set much of those forests on fire. It was, at that time, the worst fire season ever in the Arctic. The year after was actually worse. But in 2019, we had these boreal forest fires in July, and then a few weeks later in August, there were also large forest fires in the other side of the world, in the Amazon forest, where also it was hot or quite hot at the time. By the way, this map on top shows you the temperature anomalies. Red means warmer than average. As you can see, it was quite warm in these places at the time. And then a few months later, on the other side of the world in Australia, it was also hot and dry, and we had these very large Australian bushfires that I guess everyone remembers. And there were some calculations done on the carbon emissions from these several wildfires. Let's start at the bottom. with the CO2 that was released from the boreal wildfires in Russia, Alaska, Greenland, and Canada, about 100 million tons of CO2 was released during that month, more or less. And well, that roughly corresponds to the yearly emissions in Belgium. That's where I'm from. The fires in the Amazon that occurred a month later released 4 times as much. 400 million tons of CO2 were released during these fires. And then the bushfires in Australia, they were double of that. About 800 million tons of CO2 were released during these wildfires. And that corresponds more or less to the annual CO2 emissions from international aviation before COVID, so in 2018. So while these wildfires, in some places they are a natural aspect. So like in the boreal forest, and also in Australia, it's common to have wildfires, but the fires that occurred more recently are more extreme. They cover a larger area. They last longer. And well, in a tropical rainforest, it's a different story. There, large wildfires are actually not a natural thing. There is a large impact of human activities especially the slash and burn activities to clear land for agriculture. Now, after fires, ecosystems can of course slowly recover, but this recovery is slow, and it's also susceptible to climate change. During recovery, the ecosystems can sequester more carbon again, but this carbon sequestration is hindered a bit by the changing climate, because if there's a drought occurring, this of course hinders our regrowth of plants. And we're seeing now the first indications that the land carbon sink is starting to decline, so that there's still an increasing or there's still carbon being captured by the land. There's still a net sink of carbon there, but the magnitude of that sink is decreasing. So it's retarding effect on climate change is slowly decreasing. And I copied, well, on the right, there's some studies that show these first indications, and then on the left, I copied some text from the newest IPCC report, saying that the processes that stimulated the land carbon sink in the past decades are beginning to respond to the increasing CO2 and climate change in a way that will weaken nature's capacity to take up CO2. And in particular, extreme temperatures and droughts, and also permafrost thaw, which I won't go into today, tend to reduce the land carbon sink. So this is a serious threat that we need to be aware of. How bad it is or how serious a threat is depends on how much warming we allow. And this is illustrated on this figure also from the IPCC report, where these burning embers show the risk of wildfire increase and carbon loss in function of global warming. So for both, we're now in the yellow zone, which means that impacts or risks are already detectable and can be attributed to climate change with at least medium confidence. And as temperature goes up and as we approach the 2-degree limit, we enter the orange zone, which means that there is a significant and widespread impact or risk. And we really don't want to go any higher because, well, at present, we benefit from the land uptake as a buffer on climate change, but if we, if the planet keeps on warming and carbon is increasingly being released through wildfires, but also through other processes like permafrost melt, we risk losing this carbon sink and even making it a carbon source. And that will mean that climate change starts to accelerate itself. So the warmer it gets, the more CO2 is released, and the stronger the impacts on the land ecosystems. So to prevent this from happening, we need to limit warming, and preferably below 2 degrees, well below 2 degrees, like we agreed in Paris, or like the world leaders agreed on at the COP21 in Paris in 2015. The Paris Agreement was really an important milestone in the battle against climate change, and there, well, the goal was set to limit warming to well below 2 degrees and even aim for 1.5 degrees, which at that time was quite a new ambition. It was a stronger ambition that was formulated before, when the 2 degree target was what was on everyone's mind, or most people's mind anyway. Limiting warming to well below 2 degrees, or better 1.5 degrees, would give us a reasonable chance, no guarantee though, of avoiding dangerous climate warming, and especially of avoiding a snowball effect or a self-accelerating climate change. So let's have a look at what needs to happen in terms of emissions to achieve that goal. This figure shows us the historical emissions, the emissions through the burning of coal, oil, gas, and land use change over the last 150 years. Until a few years ago, these emissions were rising faster and faster. And the steepest increase was at the beginning of the 21st century, when the increase was about 3% per year, or almost 1 gigaton of CO2 per year. In recent years, emissions have been leveling off a bit, and we kind of reached a plateau now at a high level of emissions. So we're still emitting a lot, just not more and more every year. Now let's plot on the right what should happen now. The green, well, this is a figure also from the IPCC report, from the part that came out last week, the report on climate change mitigation. And the green-blue line illustrates how emissions should evolve to limit warming to 1.5 degrees. The purple line is what should happen to limit warming to 2 degrees. And I've rescaled the figure so that it matches the figure on the left. So this makes clear that the right-hand curve is quite a bit steeper than the left one, and that emissions should decrease faster than they ever increased. Specifically, to limit warming to 1.5 degrees, emissions should almost halve by 2030. This would actually bring emissions to in 2030 to the level that they were in the 1970s. And it also implies that they should fall by about 7% per year, which is more than double the fastest increase we had before. So this really requires deep decarbonization fast in all sectors, so including housing, mobility, agriculture, and all sectors. And well, we're obviously not on track yet, as you can see from the red line that illustrates the emissions under current policies. And the orange line illustrates the emissions when we take moderate action. So what is needed is really strong action and well, basically it's well, the highest priority is to get rid of fossil fuels and also stop deforestation. And yeah, we need to do so fast. Now, I won't go further into that, but I just wanted to emphasize the importance of reducing our emissions and getting rid of fossil fuels before moving on to the next part. And that is net zero emissions and negative emissions. So we need to reach net zero emissions by 2050. And after that, we even need to remove CO2 from the atmosphere, so creating negative emissions. There's only very few scenarios that allow us to limit warming to 2 degrees Celsius without any negative emission technologies, and there's no scenario that does that for the 1.5 degree scenarios. So it's ever more clear that we really need these negative emission technologies. So I want to spend some time on that. Let's look at what technologies we already have, or which we might want to work on in future in the next years and decades to capture CO2 from the atmosphere. So there's several negative emission technologies on the table. For some of this probably sounds like very technological, and you might first think of the so-called CO2 vacuum cleaners or direct air capture with carbon capture and storage. This one. But actually, there's also quite a few that are based on natural processes, so that we can use to capture CO2 from the atmosphere. And some important ones are listed here, and I will go into the ones that are land-based, so the ones that are based on natural processes. I'll go into those in more depth in the next slides. So the first one, afforestation and reforestation, is probably also relatively well known. Trees take up carbon as they grow, and by planting more trees, we can take up CO2 from the atmosphere. That's the quite simple reasoning behind this. Well, it's not that simple, but I'll go into that later. A second one that has been proposed is soil carbon sequestration. The basic idea is that we improve soil management, especially in agriculture, to increase the organic carbon stocks, because agricultural land has lost a lot of carbon due to agricultural practices, and now we want to revert that actually and increase the carbon content of the soils. For example, by avoiding deploying, by leaving residues on the soil, by planting cover crops. There are several ideas of how to improve soil carbon sequestration, but it's not that simple. It's not very clear yet what works, when, and for how long. And there's still a lot of work to do to really get a grip on how to massively increase soil carbon stocks. But if we can do it, it's not only beneficial for climate, it's also beneficial for agriculture as such, because the organic matter in the soil is important for water and nutrient retention, and it can increase crop yields then, and also climate resilience, because when your soil holds more water, of course, you're better protected against droughts. A third technology that has been proposed is the use of biochar. Biochar is what you get when you burn biomass, but taking away the oxygen, so a process called pyrolysis. And then you get this char that you see in the picture, which is a very stable form of carbon, and it can also be added to the soil as a soil improver. It's very stable, so in terms of carbon sequestration, this works quite well. It can be a soil improver, but that really depends on where you put it. In the soils in Europe, for example, it doesn't help much for improving crop yields, but in strongly degraded soils like those in Africa, it can have a strong positive effect on soil quality and fertility, and it can increase crop yields, even on top of the fertilizer effect when they have that. It's maybe also worth mentioning that biochar is currently, well, it's possible, it's available, the technique, but it's not economically viable at the moment, which is one of the reasons why it's not being deployed much. Fourth technique that's on the table is bioenergy with carbon capture and storage. So basically, you grow biomass like poplar trees or miscanthus or some other fast-growing crop, and you harvest it, you burn the biomass for energy, and the carbon that is released during that process is then stored somewhere, for example, in a geological reservoir. The problem with this technique is that large areas of land would be needed, preferably fertile land, of course, if you want the crops to grow well. And that way, this technique competes with land for food production, and also with nature, of course. So there has been quite some criticism on this technique for that reason. And then the last technique I want to go into is enhanced weathering of silicates. This is probably new to most of you, at least. Enhanced weathering of silicates is actually, or the idea is based on a geological process where silicate rocks have been reacting with water and CO2 to sequester carbon. And geological scales, this has been an important process in stabilizing climate. And the idea behind enhanced weathering is to speed up this process a million times by grinding silicate rocks and spreading this rock dust, for example, on agricultural land. I have another slide about this technique. Well, this technique is one that I've been working on in the last few years, and we have several experiments running for. So on the top right, you see a farmer spreading silicate rock powder to his field. So it's very similar to liming, but instead of lime, there's silicate rock powder being added. And applying silicate rock powder can provide several benefits. So on the one hand, there's of course the CO2 uptake, which helps for climate change mitigation. But there's also possibly a reduction of the N2 emissions, which adds to the climate change mitigation effect. These things are not yet very interesting for the farmer. So, but there's other effects that are. Silicate rock powders contain nutrients like potassium, calcium, magnesium, phosphorus, zinc, iron. It depends a bit on which rock is added, but there's various nutrients important for plant growth that are in these rocks. No nitrogen, though, but several others. And these can stimulate plant growth, crop yield, the nutritional value. It can also help in abating hidden hunger, which is the lack of micronutrients, or not a lack, but a reduction of micronutrients in our food. Silica which is an important element in the silicate rocks, of course, can also improve the drought resistance of plants by through its impact on plant structure. Another advantage that this silica has, and also other weathering products, is when it leaches out to the water, it's beneficial for the life in the water, the diatoms and other water organisms. They benefit from the release of these weathering products. On the other hand, nitrogen losses can decrease, and so nitrogen leaching, which is often a problem in Europe and US, where over-fertilization causes nitrogen losses and eutrophication. Well, these nitrogen losses may also be reduced through the changes in the soil caused by silicate rock addition. So I mentioned a lot of could, would, and so on. That's because all these effects are really unclear at the moment. It's not very, there has been little experimental research done yet on this technique. That's also a reason why in Antwerp we decided a few years back to start working on enhanced silicate weathering and to start some experiments with crops and testing different silicate sources and growing plants on soils with silicates. The paper from our first experiment was just published, and of course we also quantify carbon sequestration, and we found a sequestration rate of about 2 tons of CO2 per hectare per year, which is about the same magnitude as in several other enhanced weathering experiments. And we also found a slight positive effect on potato yield. And what's also good is that we found no increase in plant nickel concentration. And that's the one thing I forgot to mention, but there's not only, there's several potential co-benefits of enhanced weathering, but there's one important risk, and that is heavy metal contamination, because depending on the rock source, there might be quite some nickel and also other heavy metals in the silicates, and these could have adverse effects on the crops. But in our experiment, we didn't see any of that. But this is also something that is investigated in the enhanced weathering experiments now. Okay, so I want to go back to the negative emission technologies in general. So we will need these negative emission technologies to compensate for the emissions from sectors that are hard to decarbonize, such as aviation or steel production, and maybe also for a potential temperature overshoot. There's only a few scenarios in the new IPCC report that do not go over the 1.5 degrees. So it seems quite likely, unfortunately, that we will have an overshoot, temperature overshoot. So we will go over the 1.5 degrees, and then we need these negative emission technologies to reduce the CO2 in the atmosphere, to bring it back down. But the problem is that these negative emission technologies, most of them are still in their infancy. As I also illustrated for enhanced weathering, there's still a lot of research needed to find out what works where, when, and also to make sure that there's no adverse effects, or at least that they are limited. Also, the permanence of the carbon storage is not always evident, especially for the easier ones, like the tree planting. Wildfires are an obvious risk to that carbon storage, and also soil carbon sequestration is sensitive to disturbances. Also important is that there's no silver bullet. There won't be one of these techniques that will do all that we need. We need a combination of these negative emission technologies to have some meaningful effect, probably. The potential carbon sequestration is in any case limited, much lower than our current emissions. So it's still difficult to estimate the potential CO2 sequestration from these technologies because of all the uncertainties that we have. The estimates range between 5 and 10 gigatons of CO2 per year. That is what we could reach, hopefully by 2050 or a bit later. But that's still far below our current emissions. So actually these negative emission technologies, it only makes sense to invest in them if we also rapidly decrease our fossil fuel emissions and stop deforestation. Of course, nothing comes for free. These negative emission technologies, they come at a cost, and well, some techniques are cheaper than others, but they are not for free. And important also for the more nature-based solutions is that we really avoid adverse effects on food production and biodiversity. Maybe important here to go into tree planting, which has become kind of a hype in recent years. Save the world, plant a tree. Several media jumped onto this. Even Donald Trump wanted to plant 1 trillion trees to combat climate change, while at the same time he was still denying climate change was changing. And several companies also aim to contribute to sustainability by planting trees, like Microsoft here. Also Shell, they advertise for carbon neutral car driving, and they don't mean electric cars, but cars on fossil fuels for which emissions are compensated by planting trees. And well, this is really dangerous because it's not a climate solution. It's even worse. This is actually delaying the transition to a climate neutral society because we need to get rid of the fossil fuels. Tree planting, it would be nice if it was that simple, but it's not. Planting trees can be part of the climate solution in certain situations, but the benefits and the limitations depend a lot on the context, and multiple factors can play a role, like geographic region, local ecology, social contexts, and several other factors such as also climate change, because you don't want to plant a forest now and have it burned in 5 years from now. So it's we cannot plant ourselves a way out of the climate crisis, and that's important to realize and to make sure that the focus on tree planting doesn't distract us from other important climate solutions. And perhaps also important to realize is that actually restoring natural forests is the best way to remove atmospheric carbon. And the IPCC had a nice figure in its report that was published last week. It indicates, like how to go about this tree planting idea. The first question that one should ask is, was there a forest here in the first place? And if there wasn't, there probably shouldn't be planted a new one. Now, if there had been forests before, it should be checked if restoration is possible by consulting the local community, for example, and should be checked also if the benefits outweigh the costs. And that's not just economically, but also like in terms of water availability and biodiversity. And if all that looks good, then think of planting a native tree that is adapted to its environment. So I found this nice rule or set of rules to follow when one wants to plant trees. I think this should be of interest to several activists and practitioners. So this brings me to the end of my presentation, where I just like to list some very basic conclusions. Terrestrial ecosystems, as I've shown, they have been retarding climate change in the past, and they're still doing so. But there is a serious threat to this carbon sink due to climate change, and also due to several other pressures like deforestation. But if humanity can realize massive emission reduction, so get rid of fossil fuels and deforestation, then nature can help us in stabilizing climate change through helping us out with these nature-based carbon sequestration solutions. So I'd like to thank you for your attention, and well, I found this a very nice figure from Cécile Girardin, illustrating how it should go.
Thank you so much, Sarah. That was a great talk, and I especially like your part about enhanced weathering. I didn't know a lot about that, and that was very interesting. Also, the discussion at the end about differences between restoration of forests, where we used to have forests, which is probably a good idea, and then afforestation, which is planting trees, for example, in grasslands or savanna, which is probably a bad idea. And I like that distinction. So now we have 10 minutes for question. So please, if you have a question, feel free to write it down in the chat box or mute yourself and ask the question. I have one. So Sarah, based on that distinction between afforestation and restoration, do you think that the potential for carbon sequestration with by planting trees has been not only overhyped but also overestimated?
Yeah, well, there have been several estimates, and some estimates have indeed been too optimistic. But yeah, well, yes, this has happened, and this has also a bit contributed to the hype. And I hope that, well, it is increasingly being clarified that planting trees is a nice idea, but it's not a magic solution to the climate crisis. And we should be careful there. And there have been some cases where trees have been planted on wetland soils, for example, that store a lot of carbon, but where if you plant trees on these soils, you drain them basically, because the trees use so much water, and that way you bring oxygen into the organic soil, which is then rapidly decomposed, and you lose a lot of carbon. So you do a lot of bad things for the climate, also for biodiversity. And these are things that should definitely be avoided.
Yeah, okay, we have a couple questions. So Charlie, feel free to.
Oh yeah, thank you. I really enjoyed that talk. I have a question about the enhanced weathering. I always thought of enhanced weathering as primarily an effort to increase alkalinity and take CO2 out of the air that way through carbonate precipitation. But a lot of what you talked about were what I would think of as sort of secondary effects on nutrients in the soils and plant growth. Do you have any idea what the relative magnitude of the different effects are? Or maybe it's in the paper that you recently published.
I'm not clear about what relative differences you want to.
Okay, so on the one that I think about the most is just increased alkalinity in runoff into the ocean or into freshwater bodies, which leads directly to more carbonate precipitation or perhaps less carbonate dissolution and CO2 release. So that's on the one hand, and then the other hand, it seems like there are a lot of benefits from organic carbon accumulation or other uptakes of carbon directly in the soil itself.
Yeah, that's a key research question that we're trying to address, but that will depend a lot on where you're working. I think what kind of soil, what kind of plants, what kind of climate you're in, but there's really no answer to this yet. There has been no experiment that I know of, at least, that has looked into the effects of enhanced weathering on organic carbon cycling. This is something that we are planning to look into. In our previous experiments, we've seen some changes in the DOC, so the dissolved organic carbon in the soil. The dissolved organic carbon leaching increased, which could be a good thing too, because it could mean that you bring the carbon to the deeper soil layers faster, where it can be stored for,
Did you track the alkalinity or the content of base in the discharge from your experiments?
How much that was, or?
Yeah, because you can just calculate ultimately how much CO2 will be pulled out of the atmosphere by that release.
Yeah, so we did that calculation, and that for our experiment that was 2 tons of CO2 per hectare per year.
Oh, okay, that's the 2 tons was that.
That was, sorry,
okay.
that was for the inorganic carbon sequestration. So sorry, I wasn't clear about that. So that's really based on the inorganic carbon only. It doesn't take into account any changes in the organic carbon.
Okay.
Thank you, Charlie, for the question. We have a question in the chat box from Rishi. Is there a link between the global population movement towards urban areas and terrestrial carbon uptake?
Probably, but I don't know actually. For climate and for biodiversity, it's beneficial if more people live in cities and less at countryside, because it's just more sustainable, because you have everything more concentrated in one place, in the city. So in that sense, there is a relationship, but I'm not aware of studies.
I would say probably at a global scale, it doesn't play a huge role. Probably locally, in cities, there are higher levels of CO2 because of traffic, and that could lead to potentially increases in carbon uptake in cities. But the role of that at a global scale is probably minor, because we think that it is tropical forest and natural forest in general the main drivers of the land sink. But thank you for the question. There's another question. When considering the mining of silicates, transportation, grinding, etc., does enhanced weathering still have a net negative carbon impact?
Yeah, that's a good question. there's still research needed to quantify all that well, but it also depends on where you do the enhanced weathering. But yeah, there is definitely it's definitely a good balance. There have been some calculations based on available data, and there's a clear benefit of the enhanced weathering. But yeah, it depends on how far you have to transport the silicates, for example, how much energy you need for the grinding, or because at the moment, much of the silicates materials that are being used are waste material. So then, yeah, it doesn't cost extra energy to mine for it because it comes with other mining activities. But if you want to apply this at large scale, this will play an increasing role. But of course, then we also need the energy transition to come in at the same time. But overall, it seems quite clear that there is an advantage climate-wise to employing enhanced weathering. There, yeah, only a fraction would be, emitted, or only a fraction of the CO2 that is captured would be, emitted in the production